When some of you see the notion of affinities, you might immediately want to associate this notion with the linearity of a map. As a matter of fact, as you have seen in the linear algebra or Euclidean geometry, an affine map is linear if and only if it fixes the origin. And that is our proposition number 2. F from E to F is affine if and only if T from E to F defined by T of x equal to f of x minus f of 0 is linear. And now let's prove this. Although this statement may look very intuitive for you, the forward direction may be a little bit tricky. So let's first prove the backward direction. For any t in R and a, b in E, f of 1 minus t times a plus t times b is equal to, let us break this down according to this definition of t. So this is f of this guy minus f of 0 plus f of 0. So this part will correspond to our t. And now, by the linearity of t, which is our hypothesis, this guy will be equal to 1 minus t times f of a minus f of 0 plus t times f of b minus f of 0 plus f of 0. And this last line will be equal to, if you cancel out those f0s, you will end up getting just 1 minus t times f of a plus t times f of b. And this completes the proof of the backward direction. As I said earlier, the forward direction might be a little bit tricky. We start with the affinities of f and want to prove the linearity of this t, which is a translation of f by f0. And we are going to start with just a definition. For the forward direction, let us take any lambda in R and xy in E. So let us first look at t of lambda x. This guy by definition is equal to f of lambda x minus f of 0, which is further equal to f of lambda x plus 1 minus lambda times 0 minus f of 0. Here, we are going to create a linear combination. And it seems to us that the only choice will be to add a 0. So this guy is equal to lambda times f of x plus 1 minus lambda times f of 0 minus f of 0. And in the end, you will get lambda times f of x minus f of 0, which is lambda times t of x. And this shows that the map T commutes with scalars. This is the easy part. The hard part is to show that T preserves the addition. T of x plus y by definition is equal to f of x plus y minus f of 0. And t of x plus t of y by definition is f of x minus f of 0 plus f of y minus f of 0. And we want to prove that they are equal. And to this end, again, we are going to use some geometric ideas. The goal is to combine those two guys so that we can compare it with the first line. We are going to look at this picture. Say this point is f of 0, and this is f of x, and this is f of y. So this vector plus this vector, which is this guy, will be equal to, so in R2, their sum will be this vector, this diagonal line in this parallelogram. And we want to show that this diagonal line is precisely this guy. Or in other words, this point is precisely f of x plus y. Although that is not so obvious to us, we may look at in another way. Let us look at the middle point of this line segment from f of x to f of y. By the affinities of f, this middle point should be just f of x plus y divided by 2 minus f of 0 by the affinities of f. But we still need to realize this idea carefully. So this last line, the sum of those two vectors, this is equal to 2 times 1/2 times f of x plus 1/2 times f of y minus 2 times f of 0. And this first part will be equal to 2 times f of x plus y divided by 2 by the affinities of f, that f preserves any point on the line through x and y proportionally, minus 2 times f of 0. So this is by the affinities of f. So now it suffices to show that this guy is equal to this guy. So now let us rewrite this equation we want to prove. It suffices to show that f of x plus y plus f of 0 is equal to twice of f of x plus y divided by 2. But this is equivalent to just 1/2 of f of x plus y plus f of 0 equal to f of x plus y divided by 2, which is precisely another application of the affinities of f. And if you don't see it, this right hand side is equal to f of 1/2 times x plus y plus 1/2 times 0. So the establishment of this equality will be nothing but the affinities of f applied to the points 0 and x plus y. So we are done.